All right, so this lecture today is going to be kind of in two parts. The first part, we're going to finish our discussion of numbers by talking about significant figures in calculations. And so we've addressed this to some degree in our previous discussions. We're going to formalize a lot of what we say now here. So one of the first things that we're going to talk about is when it comes to significant figures, when it comes to doing calculations, the one thing that we want to try to eliminate, that we want to try to kind of limit as much as possible, is the number of times that we round a given number. So when you're doing calculations in your calculator, if you've got a long string of multiplications and divisions, a long string of adding and subtracting, you're going to want to do all of those functions all in a row before you start to round the numbers. If you don't do that, let's say that you need to add two numbers together and you add them together, and then you round the number, and then you add the next number, and then you round again, and then you add the next number, and then you round again. Every time you add or subtract, multiply or divide, every time you round a number in a calculation, you're introducing error. You're introducing uncertainty. The more uncertainty you add, the less trustworthy your number in your calculation is at the end. So when we are doing calculations, we want to keep that in mind. Round less, calculate more. The second guideline that we want to abide by is something called the weakest link principle. The weakest link principle, when we apply it to rounding, is talking about we never want to introduce or create greater precision in a calculated number than what was present in the original measurement. So if our original measurement has 4 significant figures, by the end of the calculation, we're going to want to make sure that we have no more than 4 significant figures. So if I'm doing my multiplication and my division, I'm always going to round according to the weakest link principle, meaning if I have a number that has 4 sig figs, and a number that has 5 sig figs, and a number that has 3 sig figs, I'm going to round to the one that is the weakest, the one that is the most uncertain. The most uncertain would be the one that has the 3 significant digits. So my final answer is going to have 3 significant digits because that was my least certain, least precise measurement. And if I follow that guideline, that will always guarantee that I'm not going to invent precision. I'm not going to go about and do things in a way that produces more uncertainty than what I started with. Now, this particular principle is applied differently to adding and subtracting versus multiplying and dividing. And we'll cover those in depth here. When we add and subtract, our weakest link principle is based upon decimal place. How many decimal places do I have? The more decimal places that are present, the more precise the measurement is. The fewer decimal places it has, the less precise the measurement is. And our weakest link principle comes about looking at where is that uncertain digit. So if I'm looking at this first example, I can see that my most uncertain digit in the first number is that one right there. The last number in any measurement is always the uncertain digit, the one that we have the least certainty on, the one that is the most estimated. So the third decimal place is the uncertain digit in the first number. The second decimal place is the uncertain digit in the second number. Well, what that presents is when I add these two together, I can see that I have an uncertain digit here and an uncertain digit there. I've got two uncertain digits as the result of adding together these two numbers. Since I can only ever have one uncertain digit, I'm going to round to the decimal place that eliminates all of the other uncertain digits as it rounds, which would be the leftmost place. And here's where my rounding rules come in. Again, we use the rule of 5 here in Chem 100. If it is greater than or equal to 5, we round up. If it is less than 5, we round down. 1 is less than 5, so we're going to round that one down, which means that the number that we report is 21.02. In the second example problem here, I have my 9 here as my uncertain digit. Remember, our rules for zeros, a 0 is only significant if it comes after a non-zero number and there is a decimal point. These two zeros, even though they're after a non-zero digit, they are not included with a decimal place, a decimal point. So neither of those zeros is significant. That means that this 9 is the last uncertain digit. Similarly, the last uncertain digit in 375 is the 5. So when I do my calculation, I see I have an uncertain digit here in the 100s place. I have an uncertain digit in the ones place. I'm going to round in the leftmost spot because that's going to eliminate all of the other uncertain digits. The digit directly next to that is a 2. That number is less than 5, so I'm going to round down. I end up getting 19,500. Now, probably one of the most common mistakes that students make with this kind of rounding is assuming that by rounding at this position right here, I'm actually eliminating those decimal points, those decimal places right there. I cannot tell you the number of times that I've seen where a student will tell me that the answer to this particular question is 195 because of getting the correct number of significant figures. You have to remember, these zeros are still important. They are placeholders. There's a very big difference between 19,500 and 195 in terms of the magnitude. And if you make a mistake like that, it's very easily correctable, but it is still very, very wrong. And in an application-oriented kind of sense, the difference between getting 195 milligrams of a medication versus 19,500 milligrams of a medication can be quite significant. So this application applies for any adding or subtracting kind of construct. Now, more often than not, you're correct. More often than not, you're going to be dealing with numbers and measurements that have the same exact precision. So if I'm measuring something on the balance, it has 2 decimal places precision, and I'm going to subtract it from another measurement that had 2 decimal places precision. I'm just going to carry 2 decimal places throughout that subtraction. Where this comes in handy is when we have mixing of units, or we have objects that are measured on different instruments that have different levels of precision, and we need to know what the appropriate amount of uncertainty is. That's where this kind of comes in. In a purely academic laboratory kind of scenario, you're right. More often than not, we're going to be measuring things on the same instrument, and they're going to have the same precision. And so some of that is a moot point, but that doesn't describe every scenario. That's why we have to go through this kind of exercise. Any other questions? So that's adding and subtracting. What about multiplying and dividing? Well, with multiplying and dividing, what we're looking at is instead of decimal places or figuring out where we are, what we need to look at pure and simple is the number of significant digits. So in cases like these, and this is actually far more common, where we're doing unit conversion or we're doing some kind of measurement analysis, and the precision values are going to be different. If I'm finding the density of an object, I might know the mass to 4 significant figures, but the volume to only 2. Because my mass measurement on a balance gives me 4 significant figures, 20.45 grams, but my volume is measured in a graduated cylinder that's only capable of giving me 2 significant figures. So this rule is far more commonly applied much more broadly. You're going to use this rule far more often in lab than you're going to use the adding and subtracting rule. Number of significant digits plays the role here. We're going to round to the value that gives us the fewest significant digits based upon the measurements given. So in this example, 9.19 has 3 significant figures. 3.171 has 4 significant figures. 1.0 has 2 significant figures. The weakest link principle says we need to round to the fewest Sig Figs available, which would be 2. That means I need to round to the second significant figure, which is that 9. I look at the 1 that is next to it. I need to round down. End result, I would report that the product of those 3 measurements is 29. Again, the thing that matters the most there is the number of significant figures. This value here, because it only has 2 significant figures, is going to play the biggest role in reducing the number of sig figs that are available. And as I said, in lab, we're going to apply this one much more broadly, because when we take measurements of different kinds on different machines, different pieces of glassware, they all have different levels and varieties of precision. And the chances of having a measurement of mass with 4 significant figures and a measurement of volume with 2 or 3 significant figures is far more common than having everybody have exactly the same number of sig figs. All right, any questions with this? All right, let's try it out. So my first problem, 14.6608 plus 12.2 plus 1.500000 times 10 to the second. Now, this scientific notation here, we can bring out, it would be 150.0000. We're adding and subtracting. So it's the number of decimal places that ultimately makes the difference. The last significant digit is in the 4th decimal place here, the 1st decimal place here, the 4th decimal place there. I add those 3 numbers together, 14.6608 plus 12.2 plus 150.0000. My calculator spits out 176.8608. Here's where I have to use my rules for significant figures, though. In the first and the last number, it's the fourth decimal place that is the estimate. In this number in the middle, it's the first decimal place that's the estimate. That's the one that we're going to have to round to. I look to the immediate right. I see a 6 there. That tells me I need to round up. So my result, 176.9, is the result of that addition. It's all about decimal place. This decimal place is more to the left than the other one. That's the one that we have to round to. In the second example, this one we've got to combine what we were talking about on Monday with our calculations. So I have 5.5 times 10 to the minus 8th multiplied by 4 times 10 to the 10th divided by 6.65 times 10 to the 45th. Okay. Here's where that information about how to input scientific notation is going to be really important. My first number, 5.5 e negative 8 multiplied by 4 e positive 10 divided by 6.65 e 45. I put that into the calculator, I get that big long mess of a number. The question here is not what the answer is, that's part of it. How many significant figures do I need to carry out? How many am I going to round to? So for that, I have to turn my attention back to the problem here and see, okay, this number in scientific notation had 2 sig figs. This one had 1 sig fig. And this one has 3 sig figs. My weakest link says that I need to round to the fewest, which means 1 significant figure. And so what I report as the answer then is going to be three times 10 to the negative 43rd as my answer. So once you get the hang of it, doing these kinds of calculations, these manipulations, it's not too terribly difficult. However, you got to kind of put the work in. You got to do some of the practice. And that just comes with time. So, you know, if you're looking ahead to things like the Chapter 1 homework, the post-lectures toward the end of the chapter, that's where you're going to find some of this kind of practice. And that's really what the focus of a lot of the work in the Chapter 1 quiz is going to be about as well, is how do we use numbers, significant figures to show, to demonstrate calculations. Any questions before we move away from numbers? Dale, am I, are you okay? Okay. There's a lot to take in. Like I said, the best thing I can offer you, the best I can give you is that if you get a chance to practice it, it does get more natural as you do it more often. And so that's where the homework really comes in, because the homework will give you that opportunity to practice, and the stakes are pretty low. You get to do the questions as often as you want, as much as you want. You get as much ungraded practice after as really you can tolerate. That's the best way to improve, is just to do it. Any other questions? All right, we're going to move away from numbers for a little bit. We'll come back to them on Friday when we start again looking at dimensional analysis and unit conversion and kind of getting the ground rolling there. But we're going to talk about some states of matter. And in particular, we're going to look at the three different states of matter: solid, liquid, and gas. And what are kind of the differences between them? We're going to get into some discussions of energy, physical properties, and that's going to kind of put a cap to our discussion for today. So when we talk about a solid, things that we can pull out about solids: solids have a defined shape and a defined volume. That's what makes a solid a solid. On the flip end, gases have neither of those properties. Solid, everything's defined, everything's compacted, everything's very organized and ordered together. And because of that organization, because of that rigidity in their structure, how close together the molecules are, that's how we get that defined shape, that defined volume. Gases, on the other hand, complete opposite. Molecules are far apart from each other. They take up their entire space of whatever container that we put them into. And so for those reasons, they don't have any defined shape. They don't have any defined volume. They basically are wherever we put them. So if I take a gas and I have it in a container like this, and I open that container, that gas will spontaneously start to fill this room. Doesn't matter how small the gas, how little the gas particles are, how small the sample is, it's going to try to take up the entire space as best it can. So gases have no defined shape, they have no defined volume as a result. Liquids kind of find their way into the middle. What we find is that liquids don't have a defined shape, but they do have a defined volume. The definite volume comes from the closeness of those molecules to each other. So, like solids, liquids do have molecules that are very close to one another. What makes one different from the others is the order of their arrangement. In a liquid, we see that that ordering is not present. We call those molecules disordered. And that disorganization allows those molecules to flow, to move a little bit more freely. And as a result, they kind of take on whatever shape of container that they are in. That disorganization prevents them from having a defined shape. But their close proximity to each other allows them to have a defined volume. And so that's on the atomic level how we can kind of tie the two, the ideas together. Shape is defined by arrangement, how close those molecules are to each other, how ordered their arrangement is. Volume is defined by packing. The closer those molecules are to each other, the more defined their volume is. And so we can see that in the way that we depict the different states of matter from each other. So a gas, we can see that the gas molecules here are far apart from each other. And as a result of that far apart nature, that gas fills up its entire container. All of the area in and around that atmosphere, the gases are going to fill it all up. Liquids and solids, we can see that they both are very, very close. All of those molecules are touching many other molecules. The difference between them, look at the arrangements. In the liquid, the molecules are all pointing in different directions. That little bit of disorganization allows the liquid to flow. Whereas in a solid, look how all of the molecules are generally forming and going in the same direction. Yeah, there's a little bit of variability, but if I look down the line, I can see all of these molecules in this line, they're all facing the same way. All of the molecules in this line, they're all facing the same way. That's that organization, that ordering that I was talking about. Yes. Okay. They are not. This appears, okay, let me rephrase. With water, we know that water is slightly more dense at its densest point, which is right around 4 degrees Celsius, than water in the ice state. And so that's the reason why this looks less compact than this, because this liquid is actually more dense than the solid is. So water is kind of a bad example to show exactly what that looks like, because water is kind of unique in that sense. But what we really need to hone in on and focus on is those orientations. How organized do the molecules look relative to each other? In here, we can see that generally speaking, all the molecules are facing the exact same way. There's a very ordered arrangement to how those molecules are. Now, does it look like they have more space in between? Yes, it does. That's primarily an artifact of that unique quirk of water, that water in the solid phase is actually slightly less dense than water in the liquid phase. But if we compare them from an organizational standpoint, which is what we're really trying to kind of focus in on here, we can see this is much more organized in the solid. than in the liquid, even though it is a little bit less dense. Ordinarily, that concept of density also is coupled with organization. More dense things tend to have a more organized structure as well as being more compacted. Water's a little bit unique, a little bit different in that regard. When we change phases, we can see that there are 6 possibilities. Most of these things are ones that we are familiar with. For example, we know that melting and freezing are the processes between the solid phase and the liquid phase. We see them often. Condensation and vaporization are ones that we are also familiar with pretty well. Going between liquid and gas, gas and liquid. These 2 up here at the top are a little bit less well known to us. We do see them from time to time. The example that is given here is actually a pretty good one, I like. This picture of deposition here, that is what happens in your freezer. If the freezer cycles on and off a bunch of times because the doors have been left open or stuff like that, if you see that crusting that happens where ice starts to kind of build around the edges of a freezer, that's basically what's happening here to a much larger degree. We can see deposition forming also in the form of when snow falls. What you get in snow is water vapor that crystallizes around a piece of dust. So it goes straight from the gas phase, the water vapor phase, to the solid phase in the form of a snowflake. And so when snow falls, that is a deposition process that is occurring in the form of precipitation. On the flip side, sublimation, ice. A good chunk of ice will actually sublime before it melts. So if you leave an ice tray out, chances are that in the time it takes to get all of that ice to melt, you'll end up with a lower volume of liquid in the ice tray at the end of the melting process than what you started with before. And the reason for that is sublimation. Some of that ice is actually going to vaporize completely, skip the liquid phase entirely before the ice can fully melt. So those are the 2 processes that we're less familiar with, solid to gas, gas to solid. We don't see them as often. One of the reasons why we don't see them as often is because they're just not as common. They don't have as many common applications. But with regard to ice, there are circumstances where we do see that, especially with water. So kind of in summary here, we can see that there's a summary table, table 1.2, that kind of gives us all of those properties, all of those characteristics, all kind of together in one place. The differences in shape, the differences in volume, the differences in volume changes and randomness of the arrangement. So they're all kind of there in summary. I'm not going to spend too much time in this section talking about symbols and formulas. We've talked a little bit about them already. We've talked about the idea of elemental symbols, the 1 or 2 letter abbreviations that are associated with a given element. When it comes to chemical formulas, all that a chemical formula is a listing of the elemental symbol and the number of atoms for that particular element in a given compound. And honestly, you kind of know this already. When we talk about water, H2O, we understand collectively that the 2 on the H indicates that there are 2 hydrogen atoms in that molecule. And that the O, having no subscript, means that there's only 1 atom of oxygen in that molecule as well. So symbology, we kind of already know this. This is kind of something that's been baked in already to what we already understand about science and chemistry in general. Something that we may not be familiar with, symbology regarding physical properties. So for example, in a chemical formula, these 4 symbols, S, L, G, and AQ, represent the 4 different possibilities for a given substance to exist in. Now, we talked about solid, liquid, and gas already. The 4th one, AQ, stands in for something that we call the aqueous state. Can anyone kind of conjure up what we might mean by aqueous as far as a physical state of matter is concerned? Yes. No. Mercury we would consider to be a liquidous substance. It would just be given the symbol L for liquid. Maybe it would help if we broke down the word. Aqueous. Kind of sounds like aqua. What are we talking about when we talk about aqua? What? Water. If we describe something as being aqueous, that means that it is dissolved in water. That's what aqueous is referring to. Something that is dissolved in water. So each of those different substances, each of these different ideas, if something is described as aqueous, that means that we've dissolved it in water in some kind of way. And there's a lot of cases. We'll see a lot of examples of aqueous chemistry throughout the semester, because dissolving substances in water is a really great way of getting them to react. It's a very easy way to stabilize a substance and to allow it to get into a medium where it can react. And so here are just some examples of those symbols in action. Seeing helium in the gas phase, silver here in the solid phase, carbon dioxide and methane, natural gas, both in the gas phases as well. And this is where we'll pick up on Friday. So on Friday, we're going to do a brief buzz through on physical and chemical changes and properties, which is actually the subject of that next post lecture, which is due at the end of the week. And also we'll get into talking about energy, and we'll get into the last part talking about numbers and conversions and significant figures and all of that application stuff there. So that's where we're going. Anybody have any questions? Yes. Okay, that is in Blackboard right now. That the elements proficiency you can take in Blackboard at any time. You have unlimited attempts on it. So there are 20 questions. If you get 14 right by the end of I believe it's next Friday, you actually get bonus points. So You can do that at any time. We will not be doing it in here. It will be a Blackboard exclusive. So you do need to get Proctorio set up. That's relatively simple. You just need a Chrome, webcam, microphone. If you don't have one of those things, library has access to a number of webcams at some of their stations you can use there. Have a good afternoon.